Hi, welcome to Chapter 10. So we're going to start with 10.1, which is on geometric figures. There's a lot of geometric vocab in this section, and you'll definitely find that some of it is definitely applicable to elementary school, some is applicable more to middle school, and then some even you'll find in a high school geometry class. We're not going to get into proofs like a high school geometry class would, but we'll definitely touch on some concepts that you'd find in a high school geometry class as well. And the reason we do this is it just gives you some context and some knowledge of the concepts that your elementary school students are going to encounter after they leave your class so that you can adequately prepare them in elementary school. So let's just start with a point. So a point is a location on a plane. And I probably should have defined plane first. So plane is down below, which is number 3. But you can think of a plane as an infinitely large flat surface that technically has no width. But if you look around your room, the room that you're sitting in right now, you could think of like the ceiling or the walls or the floor. It's a plane. It's part of a plane. So a plane goes infinitely in all directions. But you could think of those pieces to your room as like planes. Or if you think of like a cereal box, like if you take a look at this rectangular prism that we have over here, that's comprised of 6 planes. So there's a top, a bottom, and 4 different sides. So a point is just a location on that plane. And where that usually comes up, we've seen this before, is points on, a line, or a line segment. That line is also a part of a plane. You don't see it, but it's there. Or this rectangular prism, we talk about vertices. So this is something that we talk about starting in kindergarten. So we say, okay, how many vertices does this have? And usually in kindergarten, we're not dealing with 2-dimensional shapes. Usually we're looking at, or 3-dimensional, usually we're looking at 2-dimensional shapes like triangles. And we ask the kids, how many vertices does this have? And they say 1, 2, 3. And so vertices are just points. Collinear points that's a term for 3 or more points that lie in a single straight line. So some examples here. It says name 2 sets of collinear points. So C, B, and A would be one example. Another example would be E, B, and D. Okay. I've mentioned line segment above and already line, but let's go ahead and define those as well. So line versus line segment. So a line extends forever in both directions, and you know that it's indicated by the arrows. So if you see the arrows, you know it goes on forever in either direction. Whereas a line segment is going to have endpoints. Now it's possible, like down here, I say don't be fooled. Sometimes, you might see a picture like this, and there is a line segment within the line. So you could reference and you could say, okay, let's get our rulers and I want you to measure line segment CD. And the way that you would write that is with a line on the top, and nope, you don't actually have to, you don't put points, but you don't see any arrows. So if you don't see any arrows, that refers to line segment CD. That's measurable because it has an end point, 2 endpoints, a start and a finish. I could also say, take a look at line CD, and then at that point, I'm referring to the entire line. So you have to be specific when you're referring to certain parts of pictures. And pictures like this, we could be referring to a line or a line segment because it's possible to look at either. So just to back up though, in terms of the symbols that you use, if you want to write a line like this line above, we can call it line AB or BA, and notice we put a line with arrows on the top there. And it doesn't matter which way, whether you write it AB or BA, it refers to the same thing. Sometimes it can be a little bit more complicated where maybe you have more than 2 points. And so if you wanted to name this line, you could use any of those points. So you could call it AB, you could call it BA, you could call it AC, because think about it, if you draw a line through AC and it goes on forever, isn't it the same picture that you would get if you connected AB and that went on forever? And it is. So AC is essentially, the line AC is the same as AB or CA, or you could write BA. Oh, we already wrote BA. You could write, let's see, CB or BC. So those are your options there in terms of writing that line. And then just like lines, line segments can also, you can go either direction. So you could call it line segment AB or BA, but just remember that the line above those is going to have, it's not going to have arrows, and that represents a line segment that actually has a beginning and end. So you can measure, these are measurable because they have a finite length to them, whereas lines do not. So I mentioned plane before. It's an infinitely large flat surface. Really, where you need to think about, or I guess be concerned about planes or understanding what a plane is just enough so that you can reference parts of figures, like parts of three-dimensional figures. So for example, this prism is made up of 6 different planes. And so if you wanted to write down, if I asked you, name the planes that are in this figure, you need at least 3 points to name a plane. And this is why. If you said, well, it has plane MP. Well, MP is a part of 2 planes. MP is a part of the side of the box, and it's also a part of the top of the box. And so MP isn't specific enough to refer to one plane. Now, if I said MPO, at that point, the only plane that those 3 points specifically are a part of would be the top of the box. So that's enough to know, okay, I'm referring to the top of the box. I could also use MNO. Well, you know what, let me erase this so I can see. MPON. I could say plane MPON, and that also refers to the top of the box. So at least 3 points. You could use more if you would like. So the list here is just the different planes that are part of the box. So MNO, that refers to the top. RST, so RST, that would be the bottom of the box. POT, so POT would be the side. And so you got an idea there. And a half plane is just half, like what you would think of. It's half of a plane. And this comes into play more in geometry when we're graphing, when we're using a coordinate grid. So if you have a line drawn on a coordinate grid, that separates a plane into 2 halves. So you've got one half on one side and the other half on the other. So if we talk about lines and line segments, we have to talk about rays. So rays are consist of an endpoint and a line in one direction. So it's kind of like a half line. So an example of a ray would be like this ray up here, and we call this ray DE. And the notation for a ray is just a line segment with an arrow on one end. And you've got to be careful. You want to make sure that the part of the line segment, the part without the arrow, so the end here, that's above the end point of the ray. So I cannot call this ray ED. That would not work, because when I write ED with the arrow going this way, that refers to the ray that starts at E and goes through point D in that direction towards D, and that's not the case here. So with rays, you cannot do you cannot use any order. You have to use a specific order of the ray. So let's look at this one. So it says name 4 rays in this figure. So this would be a great place. Pause the video and try this one on your own. I know it's a little fuzzy, but we've got M, Q, and N here. So there's a couple different rays. So we have ray Q, N, that would be that way, ray right there. Whoops, I don't know why I wrote R. So QN is one ray. We've got ray MQ, would be that ray, MQ. I could also call that ray MN because it also goes through N. So MN, that actually makes the exact same picture, so these are the same. I could say ray NQ is this ray right there, so starts at N and goes through Q. And notice when I write it, when I'm writing down the symbol, I'm always writing it horizontally. The ray is always going to go to the right, which I know sometimes feels weird because in this picture, NQ, ray NQ starts here at N and then it goes sort of to the left direction. But you always write it like this, NQ, with the arrow heading to the right when you're writing the symbol. So NQ, I could also write NM. Okay, so that's another possibility. And And let's see, I think that might be about it. So those are some good options there. That's more than 4. The reason that it's good to talk about rays is because rays are part of angles. And so an angle is formed by 2 rays. So if we want to talk about what an angle is, we have to first talk about what a ray is. So an angle is when we join 2 rays together. So we have, in this example, we have ray AB and ray AC, and they come together to make an angle. You can call this angle, name it a couple different ways. We can call this angle BAC, and this angle symbol, it's actually not a less than symbol. So if you look at your keyboard, the less than symbol looks like this. So this is less than. If you go to, this isn't on your keyboard, but usually like in Microsoft Word and a lot of programs, they'll have like a math text box, and there's the angle symbol. The bottom of the angle symbol is actually horizontal, so it's slightly different than the less than symbol. Just thought I'd let you know that. So BAC, we could call it angle CAB. I could also call it angle A. Now I can't always call it angle A, but in this case I can, because there's only one angle with an endpoint of A there. It's different if you have a picture like on the right. You would not want to call any of these angles angle K. So don't say angle K. It's ambiguous, because are you talking about this one? Are you talking about this one? Are you talking about the large angle? We don't know. So if it's ambiguous, you can't use just the endpoint. If there are numbers that are inside of the angles, like here, you can say angle 1 and angle 2. So you can call this one right here, you can call it angle 1, or you could call it angle LKS, or you could call it angle SKL. So SKL, LKS. You've got some different options. This angle you could call angle 2, or you could call it angle SKY, or you could call it angle YKS. So you've got some options there. And then there's also the larger angle. So LKY is also an angle in this picture. LKY is also the large angle. Larger angle. Okay, so a couple different options in terms of naming angles. And if you ever want to add numbers in your picture, it's totally fine. So like, I know a lot of times, like with the homework, you might see a picture, where there's a lot of different angles. If you want to copy it down and write, some numbers in there so that you can quickly identify an angle, that's okay too. Sometimes that's a lot quicker than using the letters. So couple different types of angles that we should talk about. So there are 360 degrees in a full circle, and there are different angles that you can make within that 360 degree circle. And I'm going to come back to reflex. I'll do that last. So if you think about this 360 degree circle and you think about the center, let's start here to the right. If I were to make an angle that's less than 90 degrees, so 90 degrees is right here, that is what we call an acute angle. So an acute angle is, it's greater than 0, so it's not just a straight line, but it's less than 90 degrees. Okay, so it's a less than 90 degree angle. So this would be an acute angle, what I drew here, that angle right there, acute. As soon as I bring that top ray up to meet the 90 degrees and make a right angle, we call that a right angle. So right angles are equal to 90 degrees. If I take that ray and I move it even further, but not quite to 180, 180 would make a line, then we call this an obtuse angle. So an obtuse angle is greater than 90, but it's less than 180. Okay. Then once I move get my circle back here. Once I move that ray to exactly 180, then I have a straight line or a straight angle. So we say straight angles are equal to 180. And then last but not least, this is the reflex angle that I think fewest people probably hear about. or maybe even remember from when you were in school. So if we go even further, anything more than 180 we call a reflex angle. So if we take this ray here and we keep moving it around, if we move it more than 180, so more than 180, and the only way we know it's more than 180 is if you have this circle that's showing you where it's moving. So like right here, the circle is showing you that it's going more than 180, then we call that a reflex angle. So a reflex angle is greater than 180 degrees and it's less than 360. If we went all the way around to 360, then we wouldn't have an angle. It would just be one ray. So the tricky thing about a reflex angle is if you look at it from the other direction, then we have a different type of angle. So for example, I'll get a different color. If we go this direction, that's called an obtuse angle, okay? But then the blue side is called a reflex. So you really need to have that in order to identify a reflex angle. It's good to have that arrow to show you how far exactly that ray is traveling. And then, you know, ideally, it's harder in a virtual setting here, but, you know, ideally we'd be using a protractor in class and we'd be learning how to measure these angles with a protractor. So like I said, there's 360 degrees in a circle. There are some measurements that are smaller than a degree, and I thought I'd mention this. We don't actually do this in class because you can't see this on a protractor because it's too small, but I just thought it'd be interesting to add so you know. There are 60 minutes, kind of like time, but different, in every degree, and then 60 seconds in every minute. So when you're measuring degrees with a protractor, you can actually, if you see the zoomed in picture here, this is just from the textbook, you can actually measure in smaller increments than degrees, and that's minutes and seconds. This isn't something that you're going to have kids do by any means because you can't usually see these with a naked eye, but just thought it's interesting that I'd mention. So a couple other types of angles or properties of angles that are good to talk about. So complementary versus supplementary. So complementary angles are angles that together add up to 180 or visually they make a right angle. So the angles 1 and 2 in this picture, they're complementary angles. They're also considered adjacent since they're next to each other. They share a side. So these are called 1 and 2 would be adjacent complementary angles. So angle 1 and angle 2 are adjacent complementary angles. Okay. In this picture, 3 and 4 are adjacent supplementary angles because they're next to each other and they add to 180. So angle 3 and angle 4 are adjacent supplementary angles. One thing that I always tried to think of when I was younger and I was having trouble remembering the difference between complementary and supplementary, I always remember that C comes before S in the alphabet and 90 degrees is smaller than 180. And I know it seems silly, but that always helped me remember that complementary went with 90 and supplementary went with 180 when I had trouble remembering that. Vertical angles are angles that are not adjacent to each other. They're across from each other, opposite from each other, and they're formed by intersecting lines. So in this case, angles 2 and 4 are vertical. So they're formed by intersecting lines and then they're opposite from each other. And angles 1 and 3 are opposite from each other. These angles, vertical angles, are always congruent, which means that they're equal. And the way that we can label congruency is we can, and we'll talk about this in a later section, but we can even put some dash marks here. And it doesn't matter how many you use as long as they're the same. So this shows that angle 1 is congruent with angle 3. Angle 2 is congruent with angle 4. And the reason why they're congruent, let's talk about that for a minute. If you think about this entire angle, that's a line or 180 degrees. This angle right here, that's 180 degrees. So you know that 2 and 1 add up to make 180. So angle 1 plus angle 2 equals 180. Well, you also know that we can come over here. Angle 1 plus angle 4 equals 180. And what we know is that if they both equal 180, then these equal each other. So angle 1 plus angle 2 is the same as angle 1 plus angle 4. Well, if we can eliminate the angle 1s because it's the same on either side. And we know that once we do that, angle 2 equals angle 4. So what I just did is just a basic proof that shows angle 2 is equal to angle 4. And you can do the same proof with 1 and 3. So vertical, it just shows that vertical angles are always equal to each other in measure. You just have to make sure the lines are intersecting. So this is an example over here of a sneaky picture that appears as if there's vertical angles. So it seems like these should be vertical because they're across from each other, kind of like 2 and 4 are, but notice that they're not, these angles are not formed by intersecting lines. You've got a line here, and then you've got 2 more line segments coming in. So there's actually 3, you could say this is a line on the bottom with 2 line segments. So they're not vertical because they're not formed by 2 intersecting lines. So let's look at example 1. So this would be a great place. Pause the video and see if you can answer these ones. So it says list 2 pairs of adjacent supplementary angles. So I'm going to look for angles that form a line. Supplementary means 180 degrees. So I'm just going to find a line in the picture. So maybe I look at this line right here. Okay, and I need to find 2 supplementary angles. So one option might be FOE. So angle FOE. I'm going to make that a little bit lighter. So FOE, and then FOB. So FOB and FOE together make 180 degrees. And angle FOB. There are certainly other options, but that's one example. So just make sure your angles are next to each other. So notice that these share a ray. So they share this ray right here down the middle, and they add to 180. Oh, and it asks for 2 pairs. So let's do one more. So let's identify another line in the picture. Maybe I look at a line that's not horizontal. Maybe I look at this line. And I'm going to use this angle right here, so which is FOA, so FOA, so angle FOA, and AOC, so AOC would be this angle right here, angle AOC, and so together they share this ray OA in the middle, and so I'll just, let me use a different color so you can see. So we've got AOC, and we've got FOA, and you can see they share that middle ray, but they add to 180. They make a straight line. The next part lists 2 pairs of vertical angles. We've got lots of options here, so you want to look for intersecting lines. So what you could do is just pick any 2 lines. So maybe this one and this one, and then once you have those intersecting lines, find those vertical angles. So like this is one, and that's another, and I drew over it, but that point O is in the middle. So if I want to write down those points, what I would do is say, write down the angles. It'd be FOA would be 1, angle FOA would be 1, and then DOC would be 1 pair. And remember, when I'm naming angles, I could also say AOF instead of FOA. It doesn't have to be in that order. And then another option, I'm going to go back and I'll do another one. So if I identify 2 more intersecting lines, so maybe I look at that line right there and that line right there. So one angle could be this angle right here, which is a right angle, and then the other one could be this one. They're across from each other. So that's just one option there. So I would name these by naming points on those rays. So EOA, so angle EOA, and angle DOB, angle DOB. And then last but not least, 2 pairs of adjacent, so that's next to complementary angles, so angles that add to 90 degrees. So you want to look for those right angles, and you can see there's that right angle in the picture there. You don't ever want to just assume there's a right angle. You want to see it in the picture. So one example might be AOB. Okay, so angle AOB, and then angle AOC. AOE, angle AOE. Okay, I could also come down and do them below, so I could say angle EOD and angle DOB there, because I know, and the reason I can assume that those are right angles is if this is a right angle right here, then this one over here has to be, because those are intersecting lines. These are vertical angles. And if this is a right angle, then next to it has to be, because that makes a line, and the same is true up here. So we've got 4 right angles that come together. So another, oh, you know what? I made some space here. Another thing that I wanted to mention that I would normally do as an activity if we were in class is 2 parallel lines and a transversal. So I know that you don't have some open space in your notes here, but you could, I would get a separate sheet of paper to just jot this down. So one picture, and this is in your book, that your book mentions, and this is a picture that comes up quite a bit in geometry. It comes up on the SAT and the ACT, and students see this quite a bit in middle school, is 2 parallel lines meaning they're lines that never intersect, and a transversal. A transversal is any line, I'll draw it in a separate color, that cuts through 2 parallel lines, like this. So this is what we call the transversal. And it doesn't have to go in that direction. So I could have drawn it. Another way to draw it is maybe I have my parallel lines and maybe my transversal is going this way. This is also a transversal. So it's any line that cuts through those 2 parallel lines. And what happens is when we make the parallel lines in transversal, we have angles that are formed. So we have angle 1, 2, 3, 4, 5, 6, 7, 8. You could kind of think of these as angles of intersection. So they look kind of like intersections of 2 highway intersections. And these angles have names. And so there's a couple of names. We've already talked about vertical angles. So like 2 and 4 are vertical, 1 and 3. 6 and 8, 5 and 7 are vertical. Those are all the same measure because we know vertical angles are the same measure. But there are some other angles here that have some special properties. So let's first talk about corresponding angles. So corresponding angles. So corresponding angles are angles that are in the same location of an intersection. So what I mean by that is like angle 1 right here, which is in kind of the top left of this intersection, that corresponds with angle 5, which is also in the top, or I'm sorry, I said top left, it's top right, and then 5 is top right as well. So one corresponding pair would be angle 1 and angle 5. Another pair would be angle 2, it's at the top left, and angle 6. So angle 2 and angle 6. Angle 3 corresponds with angle 7. Those are at the bottom left. So angle 3 and angle 7. And then angle 4 goes with angle 8. Angle 4 and angle 8. Corresponding angles are always congruent. Okay, this symbol means congruent, which just means equal in measure. So it's just a fancy equal sign that's used often in geometry. They're equal if and only if the lines are parallel. Okay, this is the symbol for parallel. So as long as those blue lines are parallel, which in my picture they are, and actually, you know what I could do is I could write that. So let's call this L, line L and M. I'm going to say assume line L is parallel to line M, then these corresponding angles are the same. So for example, if I said that angle 1 was 30 degrees, then I know angle 5 is 30 degrees because they are their corresponding angles. So another pair of angles that has a special name are called same side, and I'm going to erase this picture so I have some more room to write here. So we've got corresponding, we also have same side interior angles. We have same side exterior. We have alternate interior. And then we have alternate exterior. So let's go through those. So let's talk about same side interior. So same side interior angles are like 4 and 5. So angle 4 and angle 5. And then angles 3 and 6. So we say interior because they're on the inside of those blue lines and they're on the same side of the transversal. So angle 6 and angle 3. These angles, if you look at them, they are actually not the same. And so what we would do if we were in class right now is we'd draw a picture like this and everybody would have a protractor, and we would use the protractor to measure these angles. And we would find that like angle 4, for instance, if you look at this picture, if I assume angle 1 is 30, if this is a line right here, then 180 degrees minus 30 is 50, so this angle has to be 50. The same thing down here. If this is a line, 30 plus 150 is 180, so 8 also has to be 150. So look at the angles, the same side interior angles, 4 and 5, those are what we call supplementary. They add to 180. So if L is parallel to M, we know that all same side interior angles are supplementary. Okay, so they add to 180. So you can always assume that. So for instance, like if I had if there was a problem in the book where maybe angle 5 was labeled as 30 and it said, well, what is angle 4? You would say, oh, well, it's 150 degrees because they're same side interior. You could assume that. So same side exterior is same side of the transversal, but on the outside of the blue line. So 8 and 1 are same side exterior. So angle 8 and angle 1, and then 7 and 2. So angle 7 and angle 2. And if you look, these are also supplementary. They add to 180. So supplementary add to 180 degrees. And then last but not least, we've got alternate interior and alternate exterior. So alternate interior angles would be like 3 and 5, so they are alternate sides of the red line, but they're on the interior of the blue lines. So 3 and 5 are alternate interiors, and 4 and 6. So angles 3 and angle 5, angle 6 and angle 4. And if you look at these angle measures, these are definitely, they both look like acute angles. These are going to be congruent. So as long as the parallel lines, L and M, are parallel, then alternate interior angles are congruent. And we know they're congruent because if we think about it, angle 4 and 3 add up to 180, and angle 6 and 5 add up to 180. And if same side interior also add up to 180, then we know that these two are going to be the same. And we could write a proof for that. But the best way to do it, and this is what I would do if we were in class, is we would just measure these. We'd measure these, we'd make a picture, we'd measure it with our protractor, and we would find that they always add to 180. And then alternate exterior, so last but not least, would be like 1 and 7. So angle 1 and angle 7. And then 2 and 8. So angle 2 and angle 8. And those are both, you can see in the picture, in my picture, they're both obtuse angles. They're congruent, but remember, if and only if those L and M, lines L and M, are parallel. If you had a situation where you had two lines like this and a transversal, then none of these properties hold true. It only works if L and M are parallel. So what I would do if I were you, I know that's a lot, is I would draw your own picture with parallel lines and a transversal, and I would give number to all your angles like we just did, and I would see if you can write these down again. So identify, or even use your fingers, play a game with yourself. You know, where are corresponding angles, where are same side exterior, where are same side interior, just to practice getting those down. I would say most standardized tests for kids, so ACT, SAT, NWEA, in high school, 30% of those tests is usually geometry, and there's always several questions that involve a picture like this with the transversal. So it's good to just kind of know where your kiddos will be heading. Okay, so I'm going to scroll down where our notes pick up. which is on curves. So we spent a lot of time talking about lines. Let's talk about curves, and we're going to set ourselves up. We're talking about curves because we're going to get into polygons soon, and so we want to be able to classify different types of polygons, and then also like cylinders and cones and figures that have curves with them. So a simple curve is a curve that starts and stops without intersecting itself. So we start and it can curve around and then it stops, but it doesn't intersect itself. It doesn't necessarily have to close, but it could. A simple closed curve is one that starts and stops at the same point, so it ends up being closed. So like this would be a simple closed curve. So notice it doesn't whoops, I don't know why that disappeared. Do it again. There we go. So this one is closed, so it's different than the first one, but it doesn't, neither one of them intersect themselves. So a closed curve that's not simple, okay, closed means that there's no gaps, it starts and stops at the same point, but it intersects itself. So a closed curve that's not simple might be like this. So it starts and stops at the same point, but there's an intersection, okay. So example 2, try these on your own first. So classify each curve as simple, simple, closed, or closed. So I'm going to say this is closed. It's not simple because of that intersection point, because of that point there. This next one would be simple. It's open there. It doesn't start and stop at the same point, so it's definitely not simple closed. This one is simple closed. Starts and stops at the same point, no intersections, and then this one is also simple closed. So when we have these, we call them plane regions, but basically these examples right here are, well, this one on the left is a polygon, this one on the right is not because it's curved, but we've got this simple closed curve, okay, so which has space inside of it, and this region can be described as either concave or convex. And so the way that we tell if a region is concave, visually it looks like it's sort of sunken in like this one is, but an even better way to think of this, because sometimes that's hard to determine, is if you imagine yourself standing on this region at some point. So imagine this is you right here and you're standing at this dot. And then you should be able to put a friend anywhere else on the figure. So let's say my friend is over here. And let's say you guys are both holding an end of a string and you stretch the string so it's tight. If the string goes outside the figure, then it means it's concave. If it does not, then it's convex. So if you think about, in this example, if you think about you and your friend, you could put you and your friend anywhere on this figure. If you connected your strings and held, or one string, you both hold either end of it and you hold it tight, that string is going to always be inside the figure. So, and I could pick different places. So I could say I'm here, my friend's here, or maybe I'm here, my friend's down here, or I'm here, my friend's right here. No matter how many different ways I draw it with positions for me and my friend, we're always inside the figure. So I say it's convex. Again, concave if the string goes outside of that plane region. So try example 3. So concave or convex. So the first one I'm going to say is convex. There's no sunken in parts. If I had held a string, it would always be inside that figure. This is going to be concave. If I did my string, I could do it right here and it would reach outside the figure. And then this one is going to be convex because anywhere that I drew a string here or a line segment, it would always be inside. And then while we're talking about plane regions, let's talk about circles. So, and we're just briefly touching on just some vocab with circles. We'll get more into depth in terms of formulas for areas of circles and radius and all that kind of thing. But basically, a circle is considered a simple closed curve. It's considered convex. It has a diameter, which is the distance from one point to another through the center. So notice, if you just do one point to another, that could be anywhere. That's what we call a chord. A diameter is also a chord. It's a special type of chord that has to go through the center. So this second line that I drew, that would be the diameter because it goes through the center. The radius is just 1/2 of the diameter. So the radius would be from here. Well, it'd be from here. I'll draw it right on the diameter so it's not confusing. So the radius is in blue. It's just 1/2. And so that gives you some good vocab to use when discussing attributes of a circle. And again, we'll get more in depth with circle vocab as we go through this chapter. So like I said before, we talked about a simple closed curve because it allows us to talk more about polygons. So a polygon is a simple closed curve, so meaning like it starts and stops at the same point. So like if you start with a triangle, if you start in one spot and you went and make a triangle, you always end up where you started with. There's no intersection, so it's not like you're going like this to make a polygon. Like a star is not considered a polygon. And then the sides are always line segments, so there's no curves in a polygon. So circle is not a polygon. A cylinder is not a polygon. Okay, so let's go through this example 4, and actually this would be a great place. Pause the video, try it on your own, try to determine which of the following figures are polygons. So the first one, I'm going to say no, because there's a curve there. The second one, yes. Now, just because it doesn't look like a cookie cutter polygon, it is one. So in this case, there's 1, 2, 3, 4, 5 sides. This is actually a pentagon. So it's not a regular pentagon. So it's not your typical pentagon that looks kind of like a house. But it is a pentagon. It's a 5-sided polygon. 3, I'm going to say no because there's a curve. 4, I'm going to say no because you have it looks like there's a hole in the middle, or you start and stop at the same place, but then you have to pick up and draw again in the middle. 5 is going to be no because there's intersection. So when you're drawing it, you're going over, you're touching vertices more than once as you're drawing, and there's intersection happening. And then 6 is also going to be no because of that same intersection concept. So if we start here and we go ahead and make our shape, in order to go back and get this part, we would have to kind of go over where we drew before. And so that violates the rule of something being a polygon. So the reason we define polygons is because it allows us to then talk about specific types of polygons. So like triangles and quadrilaterals. And there's a bunch of names for all of those. And I'm sure you've heard these before, but what I'd really encourage you to do is listen with an open mind, because a lot of times we hear these terms and we use them, but we don't necessarily remember the specific definitions of what they of how we can describe them. So let's go ahead. I'm going to label, and you could pause the video at this point and see if you can label these yourself. So if we were in class, what I would do is we would actually be we would cut out all of these terms right here, and we would play a little game where we would try to go ahead and label all of these with those terms. So you could pause the video and use the list on the next page and see if you could label these as best you can. So I'm going to start with the easiest ones and then kind of work out. So I'm going to start with a rectangle, which is this one. And I also want to point out that all squares are considered rectangles. And this is a big one because I know in elementary school we tend to tell students, well, this is a rectangle, this is a square. A square, I'll label this a square, it's also considered a rectangle by definition. So a rectangle does not have to have sides that are different lengths, pairs of sides that are one longer and one shorter. A lot of times they do, but it doesn't have to. So if we look at our definitions down here of a rectangle has pairs of opposite sides parallel. The definition of a rectangle, though, is a 4-sided figure with 4 right angles. So if you have a quadrilateral, so 4 sides, by minimum, a rectangle has 4 sides and 4 right angles. So as long as a shape has 4 sides and 4 right angles, by definition, it's a rectangle. So if you look at the square, a square has 4 sides and 4 right angles, and that's why it's also considered a rectangle. So a square is a special type of rectangle where all of the sides are equal length. So what we can do is we can draw little marks on it, and that represents that they're equal length. Now, a rectangle, as you might, know, is that opposite sides are equal, so we can label it like that. But by definition, that actually isn't part of the definition. So that is part of the characteristic of a rectangle, but by definition, it's just a 4-sided figure with 4 right angles. And then let's go ahead and do there's another 4-sided figure that's similar to a rectangle and square, but it looks just a little squished, like it's tilted, and that would be the parallelogram. So this up here, top right, this would be a parallelogram. Okay, and a parallelogram is a 4-sided figure, so it's got 4 sides, and opposite sides are parallel. And a rhombus, which is down here on the lower left, also has 4 sides where opposite sides are parallel, so it's also a parallelogram. So rhombus is a special type of parallelogram where all of the sides are the exact same length. So just like a square, a rhombus is a parallelogram. It's just a special type with a more specific definition. And then we've got, let's talk about trapezoids. So there's 2 trapezoids on here. They're the other green shape. One of them is isosceles trapezoid and the other one is just regular. So let's first talk about just a regular trapezoid. So a trapezoid, and if you look at, on the next page, if you look at the description for trapezoids, it's exactly 1 pair of opposite sides that are parallel. So to mark that, what we do is we can actually use arrows, and what this shows is that these 2 sides are parallel. The opposite sides are not. If the opposite sides were parallel, then you would end up having a rectangle and it wouldn't be a trapezoid. So exactly 1 pair of parallel sides that are opposite is the definition of a trapezoid. It's also possible, I'll give you another option here, so trapezoids can also look like this, where maybe this side's parallel to this one. This looks a little different, and that can be tilted too, so it's possible to be tilted like this, where this side is parallel to that one, and maybe it's drawn like this. So it's important that we can see these, from different perspectives. And then an isosceles trapezoid is a specific type of trapezoid. So isosceles trapezoid is a specific type of trapezoid where the opposite sides that are not parallel, so you have the 2 parallel sides, but then the sides that are not parallel are the same length. And the way that we write the same length is we just put a little dash there. So that represents that this left side is equal in length to the right side. Okay, so that takes care of the 4-sided figures. Let's talk about the triangles. So let's first talk about the, let's do this one on the top here. This would be an equilateral triangle. Equilateral triangles have the same side lengths, and they also have the same angle measures. Okay, so all 3 angles add to 180 degrees. So each one of these angle measures are 60. So this is 60 degrees, 60 degrees, 60 degrees, and same side lengths. And then we have over here, we have a right triangle. A right triangle has 1 right angle. If it had any more than 1 right angle, you wouldn't be able to make the triangle. And then down here we have an isosceles triangle. And just like the isosceles trapezoid, we have 2 sides that are equal. So this side is the same as this one, and then the third side, it doesn't have to be the same, but it could. So for example, an equilateral triangle is considered also an isosceles, because the definition of an isosceles triangle is a triangle that has at least 2 sides of equal length, so it's at least. And then let's see, we've got a couple of other triangles here. We've got, we could call this one an obtuse triangle, which just means that it has one obtuse angle, which is an angle that's bigger than 180 degrees. This could also, I'm going to say, or scalene. This one over here could be, they're very similar, could be scalene or obtuse. Okay, so an obtuse triangle has one obtuse angle, and then I'll write scalene for this one just so that we can differentiate between the two. A scalene triangle is a triangle where all three sides are different lengths, and the way you could label that is you could do one side with one dash, one side with two, and the other with three. So it just represents these are different lengths. Or you could put numbers. You could say this is length of 5, this is maybe 7, and this is, I don't know, maybe 12 or something. However you want to label that to show that the sides are different lengths. And then last but not least, this triangle right here is an acute triangle, and it's a triangle where all angles are acute. Okay, so the angles are, in this case, in this triangle, they look like they're different, but it is possible, like the equilateral triangle is a type of acute triangle because those angles are all less than 90 degrees. So it's possible that they're the same, but it's also okay if they're not the same. That's not part of the definition. By minimum, an acute angle or acute triangle just has to have angles that are all acute or less than 90 degrees. So what I would do if I were you, I know that was kind of fast, but I would go back and try to do this again on your own. If you have a printer and you want to print these out and do flashcards, that would be another great thing to do to help you learn the different properties of all of these shapes. So below, we're on the last page of the notes. I like this list here, and this just goes through all of the different grades, and it talks about what each grade level focuses on in terms of shapes. And really, in the beginning grades, we're really just looking at, comparing composing shapes, meaning like being able to draw a triangle, being able to draw a square. Defining attributes means how many vertices does a rectangle have? 4. How many sides does it have? It has 4. Grade 2, you should be able to tell students in grade 2, okay, I want you to draw a shape that has 3 sides and 3 vertices, and then tell me what it is. Grade 3, we're understanding shapes in different categories may share attributes. So this is where we get to the more critical thinking where we say things like, well, if a rectangle is a 4-sided figure with 4 right angles, does a square also fit that description? Yes, it does. So we say it's a rectangle. And then when we get in grades 4, we're talking about specific like angle measures and being perpendicular versus parallel lines and the shapes. And then grade 5, classify two-dimensional figures in hierarchy based on properties, meaning we've got rectangles and then we have squares, and all squares are a part of that rectangle category. Or we can draw a Venn diagram where we draw a picture and we have squares in the middle and then rectangles on the outside. So as the kids get older, the critical thinking just gets more complex in terms of shapes. So let's do one last example together. I know we're at 52 minutes, but we can do it. So label each statement as true or false, and then if false, draw a counterexample, which is just an example that shows that it should be false. So you could pause the video and try this. So every square is a rectangle, and I would say that that's true because rectangles are 4-sided figures with 4 right angles, and that fits the description of a square. Every equilateral triangle is an isosceles triangle. True. Isosceles have at least 2 equal sides, and an equilateral triangle has 3 equal sides, and so it's going to be also isosceles. Some right triangles are isosceles. So remember, isosceles have at least 2 sides that are the same. So see if you can draw a right triangle where maybe these 2 sides are the same, but then you have that right angle. And it looks like I just drew one right there. So I'm going to say true. It is true, and I just drew an example. Some trapezoids are parallelograms. So the definition of a trapezoid is exactly one pair of parallel lines. So you can only have one pair of parallel lines. if this were a parallelogram, the opposite sides would have to be parallel and then it wouldn't be a trapezoid. So some trapezoids are parallelograms. That would be false. And this is an example. This is not a parallelogram. It's impossible to be a parallelogram. Some isosceles triangles are scalene triangles. So let's see if we can, let's think about that. So isosceles triangles have at least 2 congruent sides. Scalene triangles have no congruent sides. So I would say false. It's impossible. So, and if we draw an isosceles triangle, here's an example of an isosceles triangle where maybe these sides are both 5 and this side is 4. It's definitely not a scalene triangle. Some isosceles triangles are obtuse triangles. So see if you can draw obtuse, meaning a angle that's greater than 90 and less than 180. So let's draw an obtuse angle, and then an isosceles triangle means that 2 sides have to be the same. So see if we can draw those sides so that they look about the same, like this, and this side looks like it's different, but that's okay. So this would be isosceles and obtuse. So I would say true. A rectangle is a parallelogram. So parallelogram is a 4-sided figure with where opposite sides are parallel, and that's true of a rectangle. So I would say true. Some rectangles are isosceles trapezoids. False. Okay, all rectangles have 4 sides, and opposite sides are parallel because if you have 4 right angles, they have to be parallel. An isosceles trapezoid only has 1 pair of parallel signs. The definition said exactly 1 set of parallel sides, so it could not be rectangle, could not be a trapezoid, an isosceles trapezoid. And then 9, some right triangles are scalene triangles. So scalene triangle means all sides are different lengths. So see if you can draw a right triangle. I'll try to draw one now where all the sides are different. So maybe I draw the next side where it's much shorter, and then I've got the hypotenuse here. So it looks like these are all different lengths. So scalene and right. So I would say true. And then last but not least, we've got some scalene triangles, so every side is different lengths, are acute. So that means I've got to draw a triangle that has 3 sides that are different lengths, so different length sides. And acute means acute, all acute angles. So I could draw maybe like this. Actually, I don't want to do a right angle because that wouldn't be acute, but how about something like that? And maybe it looks like I have to do this. That almost looks like maybe something like that. So I would say true. Looks like I could do that, where I have acute angles on the inside and different lengths on the outside. So that sums up section 10.1. As usual, let me know if you have any questions.